So far, I think we have spent a little time on meshing, but probably more time on how to set up the configure and spatial databases and stuff like that. But once you get used to running simulations, you'll find that most of your time is spent putting together your finite element mesh. Unless you have a really simple problem, it's usually going to take a while to do. So, and we're going to talk, because meshing software in general was designed for engineers, which have very regularly shaped things. And in geology, we don't have that. And so we have things like topography, we have subduction faults, we have complicated fault geometry. Sometimes we include structural boundaries. So it's important to be able to know how to deal with these. So the steps that we have in creating a mesh, first we have to decide which features we really need. So this could include the ones that I just said, fault geometry, topography, sharp structural boundaries, maybe magma sources, things like that. So what we typically do for these is in 2D we would create a spline curve, and in 3D we create a NURB surface in either cubit or trellis. And these are mathematical representations of our features that in general you would like to, typically when you're building a mesh, you're going to do it more than once. So it's nice to get the important features and save them as separate files so that you don't have to spend the time to recreate those. So you save them as what we're going to talk about today is a NURB surface, and then you can easily bring it back in to create your mesh. Typically these surfaces are used to web cut volumes. This is chopping volumes into pieces. So we'll show examples of that. And then once you have your geometry all figured out, then you start putting together your mesh. So the problems I'm going to talk about today are in examples, meshing, surface NURBS, subduction. We're also going to talk about how to use the qubit sizing function option. There are, in this directory here, there are actually some other examples. I'm not going to go through all of those, but those might also be useful for people. So what we'll cover in this example is how to deal with subduction interface geometry. We're going to have a very simplistic subduction interface. We're going to have a splay fault coming off of that. And then we're also going to include very crude topography / bathymetry. So we'll have that as one example. And then we're going to talk about how to use qubit sizing function, which what Brad mentioned it, I believe, yesterday. But what this allows you to do is to have some kind of function that will control the size of your mesh. So in general, a lot of times we'll use like an analytical function, say like some kind of spherical distance from a point. I've used ellipsoidal type sizing functions. I've also used like radial basis functions. There's a lot of different things you can use. But another one, this is important more for, say, for dynamic models where you want your cell size to be proportional to like the shear wave speed. And so you might have a spatial database that gives you your shear wave velocity, and then you can create your cell size according to that. Okay, so this is the subduction zone thing we're going to do. It's really simple. So we have our subduction zone coming down here. We have a splay fault coming up here. And actually, you can't really even tell, but there is a slight amount of bathymetry and topography in here. Well, compared to a real one, it is. Yeah. Okay, and here's an example of controlling the mesh size. So this is an example. What you do, you start off with, say, a uniform resolution mesh. And then you can operate. The files produced by Qubit are actually netcdf files, and we can add information to these files. So that's what we do. We open up, we create a uniform resolution mesh. Then we open it up, we put in our cell size information into that, and this is what you're seeing with the colors here. We've added this information to the qubit output file. So this is the desired cell size that we're going to want. So then we take it back into Qubit and apply this sizing function, and we end up with a resulting mesh where, if you remember, it's coarser down here at the bottom and then gets finer as we go up to the top. So that's a simple 1D velocity model, but you can have more complicated ones. Okay, here's another example where we have an analytical function, and what you can tell is that it's related to distance from this point here. So it's just the cell size is proportional to the distance from the point. So as you get further away, we want a larger cell size. So we input this information into existing netcdf file, then read it back into Qubit or Trellis, apply the sizing function, and then we get a refined mesh that looks like this. So this is actually really handy for a lot of things that we work on. And yes. No, sorry. The reason, hexahedral is a lot harder to do geometrical stuff. So unfortunately, we're restricted to tetrahedral elements here, and that was a good point. Yeah, I do believe it works with quads, right? Does it?
It works with quads and the paving scheme and triangles and the...
It works.
Basically any of the ones where you can do the biasing functions. So this is really a replacement for specifying the grid size along curves.
Yeah, it's just you're specifying it through the volume rather than along a curve. Yeah, okay. Oh, I guess that's it. So anyway, we'll go ahead. Let me find a good, so we're gonna, okay, this is the example that we're doing, and as always, we have a Readme here, which is what I need. First of all, typically when you get the information, you'll have like, for topography, you may have a DEM. For a subduction zone, you may have contours of the depth to the interface, and that could be for other faults as well. So what we have, first of all, we have a set of points. This is the interface points.txt, and that defines our interface geometry. So we have a Python script that will read that, and then from that it will create a Qubit journal file that can be read into Qubit, and then we can generate that geometry. So that's the first part. Then we have a similar thing for the splay fault. And then finally we have the same thing for the topography and bathymetry. We're going to use slightly different techniques. Qubit has two different, or at least two different ways, more than two actually, of forming a NURB surface. The one is what's called a net surface, and this is where you have a series of first lines going one way and then lines going the other way that have XYZ coordinates, and it will then form a surface out of that net. The other way is you could just have the equivalent of a series of contours, and it can form what's called a skin surface from that. So I believe those are the two different techniques we're going to use. One or two of the other examples in the meshing directory shows there's another technique where we can go from a triangulated surface to a NURB surface. So first we're going to just look at our set of points, this file here. And it's very simple. So you can see that this is set up as contours. These are make-believe contours with 3 points per contour. So 80 kilometers, 60, 20, and then this is sticking up in the air. And the reason that we're doing that is because we're going to want to intersect that with something that's going to chop it off. So we're going up above where we want so that we can chop it off with topography or bathymetry. So we'll just we can look at the Okay, this is just our simple little script where all we're going to do, we're going to read this in, we're going to create this journal file, and then at the end, we're going to create an ASYS is the geometry engine that Qubit uses, and we're going to create a file in that format using Qubit. This is just stuff that's going to go into our journal file, and then we're looping over the contours, reading the points, and then what we do for each of these points, we create a vertex, and then we're going to connect these vertices into a spline curve. And so at the end, we'll have a set of spline curves, and then, let's see, we're doing a net surface, so we have to do it two directions. We're going first, I forget which way we're going. Yeah. A long strike, and then we're going to go up dip. So those are the two directions. And then at the end, we have all our set of curves, and we'll create this net surface. So let me open up. Oh, first we have to run that. Okay, you know what? I'm going to run all of these because they're very similar for the display and the topobathymetry. Okay, so I've run all of those, and I've created the corresponding journal file. So we have an interface net surface journal file, splace skin surface, and then a topobath net surface. Let's see, I think that's all for those. And so we'll open up Trellis. Okay, we'll make it a little bigger. And we'll first set our directory. Oops, wait. Okay, so we'll open up our first one. This is interface net surface. And you can see that all that the Python script did, it converted those coordinates to a set of create vertex commands. So we have all of these. I believe these are the ones where we have going a long strike. So I'll go ahead and just run that part. Oh, and at the end we create a curve. Okay, so we just created these sets of points, and then for each contour, we just connected them together into a spline curve. And now we're going to do a similar thing for going up dip. Okay, so this is essentially a kind of a skeleton of our subduction zone. I will say that, I mean, this is a very simple example. For a real one, you'd have much more complicated geometry, but it also takes quite a while to create the NURB surface when you have complicated geometry. So we're sticking with this for now. So then we've created all of our curves. Now we have what they call U curves, which are like the long strike curves, and V curves, which are the up dip curves. So we're telling it, create surface net, and then the U curves, the beginning curve to the end curve, and then we do the same thing for the V curves. So we have one going this way, one going the other way, and then we're going to create a net surface out of that. Okay, so there's our resulting surface. Now we no longer need those curves that we used to create it, so we'll get rid of those. So that's our surface that we have. And now we're just going to save it as an ASYS file. Okay, so that's our first one. We'll go ahead and do the splay fault now. Okay, here we're going to do very similar, but in this case, instead of a net surface, we're going to do what's called a skin surface. And I think in this case, the results probably won't turn out much differently, but in general, I think you might get slightly more robust results with a net surface, especially like if you have contours that are very far away from each other. I think it might help constrain your surface a bit better. But this is going to be a skin surface. So it's the same thing. We create our vertices. In this case, it looks like we're doing them up dip. And then so we're going to end up with a set of profiles defining our splay fault. And then we'll join them together into spline curves. So that's this. I'm running out of space. There we go. Okay, so these are the profiles defining our splay fault. So then all we're going to do is create the skin surface using those profiles right here. So there it is. That's our splay fault. And then we delete the curves that we don't need, and then we'll export that. Okay. Then the final one is our topography and bathymetry. Okay. And you can see the thing is, this is not significant, but it looks like it goes from -8 kilometers to, well, to +3. So this is again going to be a net surface. So we'll first do the, this will probably be the U curves. It doesn't matter which is which. They just have to be intersecting. So from that, you can't even really tell there's any topography, but then we'll do the intersecting surface or curves. Okay, so you can tell this is going to be pretty primitive because we only have 3 points along the dip direction. So then again, we're going to do a net surface. So we have our U curves, our V curves, and then we'll create a surface from that. Okay. And then we will just delete the curves and export the surface. Okay. So now what we've done, we've created the 3 main surfaces for our geometry. So now we can bring those all back in. And that's what we do, let's see, in our geometry.journal file. So here we're actually going to start using SI units and things like that. And what we're going to do is create a block with dimensions that we've specified here, and then bring those surfaces in. So, okay, we bring the block in, then we're going to move it, because by default, any new object you create in Qubit has center coordinates of 0, 0, 0. So we don't want the upper surface up in the air, so we're going to move it down to so that it's it's in a more reasonable position. So first, let's see. We'll just do this. This won't do anything. This is going to reset and define some parameters. Okay. So we've defined our block dimensions here.